Hello, everybody. Welcome to the next of our special series of COP conversations. My name is Tim Wollings. I'm hosting today, and I'm going to be introducing our speaker. I'm a professor of physical climate science in the physics department at Oxford University. I look at the physics of weather patterns and climate variability and change. But today is not about me. Today is about our speaker. We're very excited to have Nick Leach speaking to us today. Nick is a PhD student at Oxford studying the attribution of extreme weather events. And the idea behind this area is, as I'm sure you're aware, we have an increasing number of extreme weather events, which are having huge impacts globally. And whenever these kind of events happen, we have a lot of questions from the media, from policymakers, and also just from the general public as to what is happening. You know, why are these events happening, and to what extent are they influenced by climate change? And for a few years now, scientists have actually been able to answer some of these questions for particular classes of events. So things like heat waves and cold events, extreme precipitation, and so on, with some level of confidence. And so there are many projects doing this. For example, the World Weather Attribution initiative, which is based in Oxford. And so what we're going to talk about today is actually how do we work this out? How do we provide these answers to help us understand the impact of climate change at the moment, and then further into the future. So as I said, we're very excited to have Nick Leach talk to us today. So Nick did a master's in physics here at Oxford, specialising in atmosphere ocean physics and also in astrophysics. But he's now a PhD student in the NERC Environmental Research Doctoral Training Partnership. He's based in the physics department, and he's working in the predictability of weather and climate group with Professors Antje Weisheimer and Miles Allen. So a lot of Nick's work is essentially focused around the use of weather forecast models in attribution. So how do we bring the kind of weather and climate science communities together? And he has a particular focus on understanding heat events. So for example, like the heat waves we had in Europe in summer 2018. But he also maintains an interest in the use of simple climate models to understand things like carbon budgets as well. So Nick is going to talk to us today about how is climate influencing our weather. Just a few little admin things to note before we start. So the talk is going to last for about 15 minutes. And then after that, we'll have about 15 minutes for questions. So if you do have any questions, then please send them in. You can do this either via the chat window on YouTube or in the comments section of Twitter or Facebook. So please note we're all working off our home Wi-Fi systems. So please do bear with us if there are any issues, but things seem to be running smoothly at the moment. Okay, so without further ado, I think I'll hand over to Nick. It's very great to have you talk to us today, Nick, and so the floor is yours. Thank you.
Thanks very much for that introduction, Tim. And yeah, so welcome to my talk, in which I'm going to be talking about how climate change is affecting the weather. In particular, how it's affecting extreme weather events, and I'm going to focus on how we kind of understand and work out how much it's affecting extreme weather events. So to start off with, I thought I'd round up kind of this year. So we've had a lot of extreme weather events, and it seems like they're kind of coming thick and fast at us this year. So we saw in June, we had an extreme heat wave in Canada, where temperatures of almost 50 degrees Celsius, so 49.6 Celsius were reached. And then we had floods in New York from the remnants of Hurricane Ida. And we also saw some really extreme flooding in Central Europe. So Germany and Belgium saw some really, really heavy rainfall and extreme flooding that followed. And I thought at this point, it'd be kind of, I'm not going to focus too much on kind of this, but it's kind of worth noting that extreme events have really devastating consequences And so like they can really impact people's lives and livelihoods. And this is why this question of how climate change is affecting them is such an important one. And it's why it's really important to understand how they might be becoming worse because of climate change. And so to start off with, I thought I'd kind of round up the consensus view on what's happening to extreme weather events. So this isn't really the focus of the talk, because a lot of you probably would have already heard kind of this kind of thing. But I thought I'd start off by introducing you to the results from the Intergovernmental Panel on Climate Change, which is a large group of scientists from around the world. So they produced a report earlier this year in August on the kind of state of the physical science of climate change. And so what we know about heat waves is on this slide, is that heat waves are getting more frequent and they're getting more intense. And this is particularly true of the most extreme heat waves. So for example, here you've got a kind of a 1 in 50 year event. So an event that most people would only see once in their lifetime now occur. So something that would have occurred in sort of the 19th century once in a lifetime now occurs 5 times more often. So that would be an event that occurs about once every 10 years. And so if we then move on to what the IPCC says about heavy rainfall and droughts, we also know that these kind of events are becoming more frequent and more intense. And so, yeah, this was a very brief overview. And for more info, I'd suggest that you look into the summary for policymakers in the IPCC's 6th assessment report. And so now straight into what I'm going to be covering today. So I'm going to be talking about some of the technical details of how scientists carry out these analyses behind the headlines you've probably seen, like this one, where we've seen in this headline that climate change has made Siberian heat waves 600 times more likely. But how do we know this? And I'm going to split the talk into 2 parts. I'm firstly going to talk about what kind of I'm calling conventional attribution, which is what scientists tend to do at the moment to work out these kind of numbers. And then I'm going to be talking about what I'm doing here at Oxford with some colleagues of mine, and what I'd sort of call as the kind of cutting edge, and what we hope to do, and by using weather models to predict the models that predict the weather to answer the kind of same kinds of questions that people are currently doing, like you see in this headline. And so to start off with, I'm going to start by talking about kind of why it's important to ask the right question in attribution of extreme weather. So I've put up here is an extreme event ever caused by climate change? And so this is an incredibly difficult question to answer with certainty, to say that any single event is actually caused directly by climate change, or another way of putting this is, without climate change, an event would have been impossible. So there are actually, I'd probably say that there are an extremely limited number of events where this might actually be the case. But for the vast majority of extreme events, most scientists would probably say they're not directly caused by climate change, but climate change might be making them worse. And so this is why we actually instead ask these questions. So we ask how climate change is impacting these events by making them more intense, or making them occur more or less frequently. So how much more likely they're becoming because of climate change. And so now I'm going to quickly discuss how we kind of generally answer these questions in conventional attribution. So the title of this slide is "There is no planet B." And so what do I mean by that in this context? So in climate science, we can't perform an experiment in the real world to find out what the climate would look like if there were no humans. So if there was no human influence on the climate, there is no kind of spare planet where we can just take out all of the greenhouse gases that we've emitted over the last kind of 200 years. So instead, in order to determine what this climate without man-made greenhouse gas and aerosol emissions would look like, we turn to climate models. So these are a really astonishing feat of engineering that take all of the physics we know about the atmosphere, oceans, and other parts of the Earth system, and we use it to simulate the Earth's climate, but within a computer. And so, for example, here are 3 of the key equations that climate models solve in order to simulate the Earth's climate. So these are what we call the Navier-Stokes equations, and they describe how fluids move. I mean, these aren't the only kind of physics that are in climate models. There's a lot more physics, but basically what climate models are doing is they're taking all the physics we know about the Earth, and they're using it to try and replicate what the Earth actually looks like in reality. And so this is a schematic of what a climate model might look like. So in order to reduce the complexity of the Earth system, such that computers are actually able to solve the equations in a kind of realistic amount of time, we divide the Earth up into a number of boxes, and we solve all of these equations and processes in each of these boxes. And so how large these boxes are is called the model's resolution. And this is an important feature of a model that I'm going to talk a bit more about later on. And so the number of boxes and their size is important for how well you can simulate the climate, because many important physical processes might actually occur on scales that are smaller than the boxes that you're trying to kind of simulate with a climate model. And so this is, again, something I'm going to talk about later. And so I thought I'd finish this slide with saying climate models are genuinely amazing. And this is something that was recognized recently by the Nobel Prize for Physics going to one of the pioneers of these kinds of models. But it's always important to remember they're not perfect. And this is a fact that motivates the second half of my talk, where I'm going to talk about what I'm doing personally. So now let's go on to how kind of conventional attribution actually works. So you start off with an event, so a trigger event such as the 2018 heat wave. This is something that I've looked at myself. So this was an event that broke temperature records and caused wildfires across Europe. What you then do is you run what we call a kind of ensemble of climate model simulations. So we run a climate model, both where we're trying to simulate the real climate, where you've got human influence and you've got greenhouse gases and aerosols in the atmosphere. So you run it once like that, and then you run it again, but where you've taken out human influence on the climate. So you've removed all of the greenhouse gases and all the aerosols from the atmosphere, and you see what this looks like. And so, but it's important to mention that we don't just kind of run the model for 1 year, or we run the model once and sort of compare those two runs. What we do is we run the model lots and lots of times. So we run the model either for lots of years or for the same kind of year again and again and again, to build up a really full picture of what the climate looks like, both in the real world and also in a world without human influence. And so here, this is kind of illustrated by this figure. So on the left, you've got the kind of real world simulations. And on the right are the simulations from the same model where we've taken out human influence. And so the final step is you analyze each of these kind of groups of simulations. So I'm going to refer to them as ensembles from now on, because that's what we call them in climate science. And so you analyze these in order to determine the impact of greenhouse gas emissions on the particular extreme event. So now I'm going to blow up this figure so I can explain how we do this in a bit more detail. So these are histograms of the two ensembles. So in the red, you've got the kind of real world model simulation. And in the blue, you've got our simulation where we've taken out human influence. So on the x-axis here, you've got a temperature extreme. So this particular temperature extreme is the hottest day of the summer averaged over the UK. And on the y-axis is the number of simulations within each ensemble that reached a particular level of the temperature extreme. So it's the frequency with which each temperature occurs in our two ensembles. And you can see that in the real world, you're getting more hotter temperature extremes. And so now I can add on a black line. So this shows where our event might be. So let's say that we observed a temperature during the 2018 heat wave of 19 degrees. So this is what was seen in reality. And now I've added in some shading. So this red shading indicates the probability of an extreme at least as hot as it was observed in reality, so where the black line is, in the real world simulations. And now the blue shaded area is exactly the same probability, but in our world where we don't have any human influence on the climate. And as you can see, this area is smaller, so it's less likely. And so what we usually do is we divide these two areas or probabilities, kind of they're the same thing, to work out how many more times likely the extreme event is in the real world compared to a world where you don't have any human influence on the climate. And so this is what we call the risk ratio. It's shown in the top right. So for this particular temperature extreme of 19 degrees, it's 3.2 times more likely in the real world simulations than in the simulations without human influence. And so this is the number that you often see reported in the media. So like that 600 times more likely headline I brought up earlier, that's this number, the risk ratio. And so I can use this figure to also explain a point that I kind of skipped over earlier with the IPCC consensus for you, which is that the higher an extreme, so the more extreme an event we're seeing, in general, the higher this risk ratio is. So I can do this by creating an animation where we push this black line further and further to the right, and you can see that this ratio is increasing. So some events that have happened this year very recently, like the Canadian heat wave, so the Pacific Northwest heat wave, have taken this to the kind of right to the max, and they've pushed the black line so far to the right that they appear to be kind of virtually impossible in a world without climate change. Though it's always good to kind of point out that with such exceptional events, the uncertainties are often very large. So proving that that's the case is very tricky. And so this is that was kind of a really brief overview. So there are some more kind of fine details that scientists are that are very important to scientists, but that I'm just kind of skim over for now. And you can always check the reference at the bottom if you want to look in this in more detail. So one kind of key aspect is you've got to define an event. So if you have a really long and very hot heat wave over a large region, how do you choose exactly what kind of time period and what kind of area you're looking at to kind of say, this is my heat wave? Secondly, making sure that your model is consistent with observations. This is a really important step. If you have a model that isn't able to kind of reproduce the observations, then kind of naturally you can't really trust it, and we tend not to use the models that are just inconsistent with observations. And finally, using more than one climate model try and reduce the impact of kind of potential problems and biases that any one model might have. Yeah. And so now that's just a brief overview of what people tend to do in general. And I'm now going to talk about kind of potential problems that we see with this approach that we are trying to work on to solve here in Oxford. So firstly, it takes a lot of computing power to run these climate models, kind of the many times you need to build up this full picture of the climate in your ensemble. And so you generally have to limit their resolution. And this sets limits on the physical processes that these models are able to simulate. So this is particularly important for extreme events because by their nature, extreme events are exceptional, and they often involve a large number of different processes coming together in just the right way to produce this really unusual event. So this means that even if you have a climate model that's able to perfectly model the average climate of the Earth really well, it still might not be able to simulate one of these processes that are really important for an individual extreme event, just because of the limits you've got on your resolution and your computing power. And so this gives you a problem with using this hypothetical model to attribute this extreme event. And so my second point is a little bit more philosophical. So in a climate model ensemble, high temperatures can be caused by lots and lots of different mechanisms. So you could have so in Europe, we often get this kind of high pressure block where you get an area of high pressure that stays over Central Europe for a long time. And this causes high temperature in the summer, but you can also have other mechanisms for having high temperatures, like warm air being advected from the tropics. And so in your ensemble, you may have lots of different mechanisms that are all providing a really hot event, but they may not be the same as the one that you're kind of trying to attribute. So you might not actually be attributing the specific event, but just generally hot events. And so this attribution of kind of hot events rather than the specific event is still a really useful question to answer, but I would kind of argue that it's not necessarily an attribution of the specific extreme event that occurred. And so now I'm going to go on to how we're trying to kind of resolve these potential issues with conventional attribution. So we're proposing that you could use weather forecast models to try and answer these questions in order to make attribution of extreme weather kind of more robust. So why would we want to use weather forecast models? I've discussed resolution briefly before. So climate models have limits to their resolution set by the computational cost of running these models. And weather forecast models are almost always higher resolution. So they can simulate processes that occur on smaller scales and also simulate the climate at a more local level, which can be really important for extreme events like heavy rainfall, which can be very local. And so to illustrate this, here I've got an animation of surface winds. So on the left, you can see what a typical weather forecast model might look like. So this is what a weather forecast model might simulate. And on the right is exactly the same data, the same information, but within the kind of resolution that you get in a climate model, which is around 100 kilometers. Each box is about 100 kilometers, whereas in the weather forecast model, each box is about 18 kilometers. And so this really highlights the importance of resolution. So you've got so much more detail in the weather forecast model, and you can see why the weather forecast model might be able to simulate many more processes than the climate model, just because it's got a much higher resolution. So my second reason for using weather forecasts was that it's quite kind of easy to tell whether they can simulate a particular extreme event well or not. And so the way that we can do this is just by checking to see if the weather forecast model was successful at predicting the event or not. So if it was a successful forecast, as in that it did predict the event, this generally means that the forecast model is able to accurately simulate all of the processes and mechanisms that were important for that event because it did predict it. So this leads me into my next point, which is that rather than having this mixture of lots of different extremes that I talked about, that is what you get out of a climate model ensemble. So basically lots of very hot events, but they could be very hot for many different reasons. With a successful forecast, what you get is you get lots of simulations of the kind of actual event that occurred. So if we use a weather forecast model, we can say that we're genuinely attributing this specific event that occurred. And the final reason why we might want to use a weather forecast model is that they're extensively verified and kind of constantly improved upon. So good weather prediction is an incredibly valuable thing to be able to do commercially because of the many applications. So one of these applications is the military, which sees a lot of funding. And so weather forecasting centers are kind of constantly checking their forecast models and improving upon them. And the same is not always true for climate models, which don't really have the same commercial value and then therefore tend to be kind of limited to academic exercises. So my kind of final demonstration of this is that there have actually, like some of the extreme events I've talked about this year that have happened this year were predicted really well by weather forecasts. So in particular on the right here, this is something that came out of the National Weather Center Portland. So the Pacific Northwest heat wave was so extreme that many climate models really struggled to simulate temperatures that hot, even at the end of the 21st century in a kind of mid-range scenario, by which time the globe has warmed by around 2 degrees. So almost double the global warming that we're seeing at the present day, and they still really struggle to generate those temperatures. However, the weather forecast models actually predicted this event really well at a kind of lead time of about a week, which is pretty impressive. And so this is just kind of a bit of backing up for why we might want to turn to weather forecasts. And so what's our aim? So, and how do we propose to use these models? So in short, it's basically in a very similar way to how climate models are used. So we suggest that what might happen is you have an extreme event that occurs and you can see that your weather forecast models have predicted it successfully. And so just to provide a bit of backing for this bullet point, so when you run a weather model, you initialize it. So you start it off from what's your best guess of what the Earth system looks like at the present. So we propose that you take this kind of best guess of the starting state of your weather model, you take the impact of human influence on the climate from this guess, and you also reduce greenhouse gas concentrations back to the levels before human influence, and then you restart your model with this kind of no human influence best guess for state. And so this should result in a weather forecast of a world without human influence, so which would hopefully look something like a simulation of the same extreme event that the forecast model was able to predict, but in a world in which humanity never warmed the climate by emitting greenhouse gases or aerosols. And so finally, you then compare this kind of no human influence forecast to the actual forecast of the event in a really similar manner to how I kind of explained earlier. And so it's great to kind of propose this, but how far have we actually got with it? So we've looked at the heat wave that occurred over Europe in February 2019. This is something that if you are here in the UK or in Europe, you might remember. And so what we've done is we've done the first step. So we've rerun forecasts in a world where we've lowered CO2 concentrations, but we haven't changed anything about the kind of starting state of our model. So we haven't changed anything about the best guess of what the Earth looked like when we started the model off. So everything in our in the experiment that we've run is identical to the real forecast, except the CO2 concentration. So this means that we're looking at the direct impact of CO2 because of its radiative properties only. And it's not the entire contribution of human influence on the event, because I mean, humans have done stuff. We've warmed the oceans and things like that. And that is very important for extreme events as well. So what we're looking at here is just the kind of direct impact of CO2 only and not the full human contribution. However, we found that even the direct CO2 impact only, it has a really clear impact even on really short timescales. So this is a figure from a study that we're doing at the moment. So if you ignore the dots and look at the top left-hand panel, this is a forecast that we started off 3 days before the heat wave, so really not a long time at all. And we found that even on such a short lead time, the CO2 has a really clear impact. So we can say that if CO2 concentrations had suddenly been reduced 3 days before the heat wave happened, the temperatures that we observed in the heat wave would have been lower. And so we actually found this impact on such a short timescale, kind of speaking in terms of the timescales usually involved in atmospheric processes. We found this really surprising. And you can also see that if you give the atmosphere more time, so if you more time to adjust to the change in CO2, so going across and then down to kind of this one that was initialized 22 days before the heat wave, the impact becomes larger. However, the impact also becomes more difficult to detect due to the chaotic nature of the atmosphere, just adding more and more noise as you kind of run your model for longer. And so now I'm going to have a bit of a look at what we're looking to do at the moment. So as I've mentioned the Pacific Northwest heatwave a few times, as it is such an extreme and interesting event. And so we're actually going to look at it ourselves and see what we can work out using these weather forecast models. As I've said, it was well forecast, but most climate models struggle to generate such high temperatures that we're seen in the Pacific Northwest heatwave. And so this time around, we are going to try and estimate the full human influence on the heatwave by both reducing the CO2 concentrations like we did in the February 2019 heatwave, but also by removing human influence from the best guess state that we start the model off in. So this will involve doing things like taking the best guess state and cooling the oceans by the amount over which they've warmed over the last kind of 200 years. And so if you're interested in this kind of stuff, then look out for this work in the future. And finally, I just want to say thanks for listening. And I think now I'm gonna take some questions.
Great, thank you very much, Nick. That was a wonderful talk. I'll give you a little virtual round of applause from this side of Oxford. Really interesting to hear about this work. I think it's really great to link up the kind of weather forecasting technology with the climate modelling. I guess you highlighted the Nobel Prize awarded to a couple of people who were really instrumental in developing climate models, and that really, as you say, recognises the huge advances made in those areas. And we should also celebrate weather forecasting, right? Weather forecasting is amazing. I know, particularly in the UK, we always like to bash our weather forecasts and complain about the forecast as much as the weather, but it is incredible what they can predict. And the fact that they're tested day in and day out in terms of making actual predictions, right? These are computer models that are predicting the future over the course of a few days or weeks. And so the fact that we can now start to use these models for climate purposes, that link to having that direct testing of the ability to predict the future, I think is really useful. So yeah, it's great work. Thank you. So we've got loads of questions coming in. We'll try to do a few of them. I think I'll kind of group some of them together because we've got so many. There's quite a few people asking about the kind of likely impacts, I think, particular for the UK. So in terms of kind of what type of extremes we're expecting to see. So we've got questions from Sue and Jeremy and Rich, essentially asking what you think are the kind of most likely weather extremes that you think are going to get worse in the future. So, as well as the heat you've talked about, is it floods, fires? What kind of thing might we expect? And what are you, as a scientist, what are you most worried about?
So is it in terms of kind of the UK? Because
yeah, that's right. Yeah, I think yeah. Let's start with that. Yeah,
I can start off with the UK. So I think the IPCC Sixth Assessment Report, which I talked about a bit at the start, has some really good stuff about this. So if you're interested in this, then I'd say go there as well. But so what the kind of extremes that we're expecting to see more of and that are going to become worse over the coming kind of years if we don't stop emitting greenhouse gases are, so like I've mentioned, heat waves. We're pretty confident that these are going to get hotter and they're going to get more frequent. So heavy rainfall events is a particularly significant one for the UK. So we again think we're going to get wetter and more frequent, rainfall events that are the kind of really heavy rainfall. So this doesn't necessarily mean that we actually get more rain. It just means that the heaviest events are going to get worse. And so you can kind of see how that will also, the UK is kind of particularly at risk from the flooding extreme events. So with the heavy rainfall, this will naturally kind of lead to more potential flooding events. I think they're what I'd say were kind of the ones that I'm most worried about, I guess, for the UK. So I mean, anecdotally, like I recently moved from Reading, but I used to live in Reading, and so the Thames flooded once when I was there, and you can kind of see how much this can change like your life, because you can no longer take the paths that you used to take because they're just underwater and things like that. So this like things like floods can be really impactful. Even like if you live near a river, you should probably be a little bit worried about this. But yeah.
Right, thank you. Yeah, no, I can agree that we've had bits of the Thames lapping at our doorstep in the past, so that's definitely a worry in Oxford. I've a question from Chris. He says that he used to run a climate calculation screensaver on his work computer in the early 2000s. I expect that may well have been the project that you're involved with, Nick, climateprediction.net. So thank you very much, Chris, for contributing to that. So yeah, he said that was in the early 2000s. And his question is, how much better are climate computation, climate simulations compared to those days?
So I would say that there have been some quite significant advances. But I've talked quite a lot about resolution. So the resolution of the models that we run, the climate models we run today, are a lot higher than they were in the kind of early 2000s that you're talking about. And we've also been able to add in kind of more processes in the climate models that we run regularly. So whereas in probably the early 2000s, I mean, things like coupled models were just starting to come in. But you might have only seen kind of a model of the atmosphere where we then prescribe an ocean, kind of a sea surface temperature beneath it, and we just run the atmosphere and see what happens there. So that was what happened then. And now pretty much all the climate models run in this kind of coupled mode where they're running both a model of the ocean and a model of the atmosphere, and could also, like many of them, also run models of things like sea ice and kind of the biosphere as well. And so all of these things are kind of building up to allow us to give this fuller picture of what the climate might look like rather than any one component, and how they also interact is really important. So that's a kind of advance that I would have said that's pretty important between the early 2000s and now.
Great, thank you. One thing that I've personally found very interesting in your work is that kind of short-term impact that you said, that the kind of the direct effect of the CO2 really emerges very quickly. And so we have a question from, I don't know if it's a different Chris or the same Chris, who's also fascinated in this short-term impact. And he's asking, is that essentially encouraging news for the success of, for example, carbon capture?
So I think I wouldn't want to sort of say too much, because the kind of experiments that I've run here are not really that realistic. So what we've done is we've essentially said that it's like the experiments that I've run where I've reduced the CO2 is like saying that one day the CO2 is the present day concentration, and then instantly the next day it's back to pre-industrial levels. Whereas for kind of things like carbon capture will naturally happen over a period of time. But I would say, I don't know how much I can say about things like carbon capture from my work, but I would have said that it is really interesting how quickly the climate responds on these kind of timescales of days, rather than requiring the months that you might maybe have expected, because we tend to look at climate model simulations that go on for like hundreds of years to see the impact of CO2. But we've seen that with the weather models that it actually only takes a few days to start to see this impact. So I think overall, I'd say I don't know how much we can say about things like carbon capture with my work, but it is very interesting to see that we see the response on very short timescales.
Yeah, I agree, and I guess part of the issue here is that there's kind of several different processes going on in the response, aren't there? So we're talking now about the kind of the direct response of the atmosphere to having that carbon dioxide in it. Whereas another obvious thing that's happening is that the oceans are warming up, in particular as the world warms. And you talked about this in your talk. And so that effect, in a sense, doesn't go. If we could immediately cleanse all the carbon from the atmosphere, then we'd still, at the moment, have very warm oceans. And I guess I think that probably there's another question from Kelly, which is related. She's saying, if we achieve net zero in the way we're hoping to, say by 2050, could these extremes start to reverse? Or is that not how it works? And I guess the kind of the built-in effect of the warming of the oceans is important there. But yeah, what would you say looking into the forwards if we do achieve the kind of net zero targets we're talking about? What will happen to these extremes? So
I think the kind of best pitch that science could give you is that once we achieve net zero, kind of the Earth should stop warming. So what net zero means is that we've stopped making kind of the Earth actually increase in temperature, and the temperature should stabilize. That's kind of the best picture that we have of how the Earth system works at the moment. And what this would generally mean is that the extreme events from the point at which you hit net zero, they shouldn't become any more frequent or any more intense. I mean, like we might see kind of local changes and there might be small changes, but we will have stopped them from getting any more frequent or any worse. However, just hitting net zero doesn't mean that the extreme events then sort of start to become less likely. So this would require us to then kind of reverse climate change and sort of actively take carbon out of the atmosphere in order to cool the climate. So my kind of quick answer is that net zero means that they won't get any worse, but they won't kind of get better.
Great, thank you. So we'll just do one more question, I think. So we have a question from Greta, which is great. Thank you for joining, Greta. I thought you would have been busy up in Glasgow, but it's a good choice to come to join this talk instead. Thank you. So Greta is asking, how are the weather forecasts initialized in the non-human influence scenario? And so, for example, do these models include CO2 concentration directly, or are you translating the CO2 concentration to other weather variables?
So yeah, that's a really interesting question. So this is something I'm actually kind of working on at the moment. So the forecast models, the weather forecast model, at least the one that I'm working with, and I think probably most of the others, they do include CO2 concentrations directly. So when I've run these experiments with reduced CO2 concentrations, I've gone into the model and I've sort of reduced the CO2 concentrations everywhere back to the level that they were at before human influence on the climate. And so the next step in what I've been talking about with kind of the way the model is initialized is, what I plan to do is I take our kind of the best estimate that was used to initialize the kind of actual forecast in the real world, and then using the kind of the many observations that we've been taking of the world over the last kind of 100 to 200 years. So I mean, humans as a species, we love to observe things. And we've been observing things for a long time. So what I'm going to do is I'm going to take the observations that we have of the oceans, and I'm going to see how much the oceans have warmed and kind of every kind of level of the ocean. So I'm going to look at a 3D ocean and see how the temperature's changed over the last 120 years. And then using this kind of change, I'm going to add or like subtract this change from our best guess that we originally initialized the model from, so that we then have a model where I've both reduced the CO2 concentrations down to down to levels without human influence. And I've also cooled the ocean at every level back to kind of our best estimate of what the ocean might have looked like 100 or 120 years ago. And so does that make sense?
Brilliant. Yeah, thank you very much, Nick. That sounds like another great experiment. We're looking forward to seeing what happens.
Thanks.
Great. So we should stop there. So first of all, I'd just like to thank you again, Nick, very much for joining us. It's been a wonderful event, a very interesting talk with lots of good questions as well. So thank you very much for your time and for speaking to us. Thank you to all of our audience, everybody for joining. It's been great to have you involved. Thanks for all your questions. Hope you enjoyed today's talk. You can find links to all previous talks in this series on the webpage that's listed in the description kind of just below this video. There's lots of other great talks there to look at as well. So this is the last in the current series of our live streams, this kind of countdown to COP series. To discover more about how our climate and biodiversity research is currently playing a role at the major climate event of the year, obviously up in Glasgow, please go to the True Planet website, which again is linked below the video. Okay, so thank you very much to Nick and to all of our audience, and goodbye.